We continue now in discussing light and where light is coming from in atoms, how it's produced, how it's absorbed. Again, light is so critical to astronomers for providing information. We need to understand more about it and some of the uses of light in determining information from distant objects. Again, we're going to discuss the formation of spectra, emission spectra, and discuss absorption spectra a little bit, and talk about how elements create their unique patterns of emission and absorption lines. We're also going to discuss briefly how astronomers can determine the speed of a star or galaxy, something that is billions of light years away. So let's continue here. So we need to get into a little bit of the fundamentals of the atom. The atom is sort of a unit of matter, and atoms can be linked together to form molecules. We have different atoms available, 92 naturally occurring atoms, different atoms. Some of them be hydrogen and helium, especially important in astronomy, and then carbon, oxygen, iron, calcium, magnesium, aluminum, uranium, etc., etc. A basic model for the atom is that there's a very small, dense, positively charged nucleus. The nucleus has positive charge. And we know now that we've identified constituents of the nucleus, and we call those protons and neutrons. Protons having a positive charge and neutrons being electrically neutral. The nucleus is really where almost all the mass of the atom is located. There are electrons that are some distance away from the nucleus, held to the nucleus by electrical force. The protons are positively charged, the electrons have negative charge, and there's electric force between them. That creates this inward force that holds on, at least tries to hold on to the electrons. Electrons can be removed from atoms, but in a neutral atom, the protons will hold on to the electrons, and in this neutral atom, the number of electrons is equal to the number of protons. It turns out the charge on a proton has the same size as the charge on an electron. So if you have 5 protons in the nucleus and you have 5 electrons, you have 5 units of positive charge in the nucleus, you have 5 units of negative charge for the electrons, and the overall charge of the atom is 0. It's neutral. So here's the Bohr model for the hydrogen atom. In the 1800s, experiments were done, and the electron was identified as a negative charge particle, and people started to speculate what's the nature of atoms. One speculation that was a semi-successful speculation is the Bohr model for the hydrogen atom. It gives us an easy-to-picture model for the atom, a good point of discussion. I need to tell you it's not correct in detail, but it has a working principle to it that is useful for understanding. It's useful enough to help us understand what's happening in the atom. So the Bohr model, the electrons are orbiting the nucleus by this electrical attractive force, circular orbit here. Again, this is a model. This is not what really happens. The electrons do not orbit the protons in the nucleus in a circular orbit. We're not going to go into the full details of that. There was a big problem, though, with classical physics and this model. Classical physics, the physics before 1900, we're moving now into modern physics, the early 1900s. But classical physics has a problem with this model in saying that when charge is accelerated, it emits light. And that is true. When charges accelerate, they do emit light. That's sort of a working principle of radio. The electrons in a radio antenna are being accelerated back and forth and consequently send out radio waves. So classical physics would say that this electron being accelerated, moving around this circle, would have a loss of energy. It would be radiating off light, and consequently it would quickly have a smaller orbit such that it would spiral into the nucleus, and I think it's like a trillionth of a second would be all the time that would be required for the electron to spiral in. Well, obviously we have atoms with a certain size. Our atoms don't suddenly shrink; they're a fixed size. And Bohr had a speculation on this, a hypothesis on this, in that the electrons were in stable orbits in an atom and did not suffer from this loss of energy, this radiation, when they're in an atom. He said there's an exception. When charge is in an atom and accelerating, it does not emit light. It has a stable orbit. So we'll get to how light is emitted in just a minute. But a little bit more on atoms. So we have the number of protons in the nucleus. That tells us what the element is. That's the key parameter. The number of protons in the nucleus tells us what element that we're working with. So hydrogen has 1 proton, helium has 2 protons, carbon has 6 protons, nitrogen has 7 protons, uranium has 92 protons. So the number of protons gives us the name of the element. You probably have heard about isotopes, especially radioactive isotopes. Not all isotopes are radioactive, but isotopes do have this property. Isotopes of the same element will have the same number of protons, but the number of neutrons is different. So there is carbon-12, that's the most common form of carbon. This has 6 protons and 6 neutrons in its nucleus, leading to the 12 designation, 6 protons plus 6 neutrons. Carbon-14, the radioactive version of carbon that's useful for dating archaeological artifacts. Carbon-14 has 6 protons, it's carbon. Carbon has 6 protons, and it has 8 neutrons. So 6 protons plus 8 neutrons, we have carbon-14, and it is radioactive. So isotopes of a particular element, we have the same number of protons but different number of neutrons. Hydrogen has 3 isotopes. There's the normal hydrogen with just 1 proton. There's deuterium, that's 1 proton and 1 neutron. And there's tritium with 1 proton and 2 neutrons. So isotopes, same number of protons, but the number of neutrons varies a little bit. I'm going to actually go back to a slide here. This slide does not quite do justice to the scale of distance between the proton and the electron in an atom. The nucleus is extremely small compared to the size of the atom. The size of the atom is roughly 100,000 times the size of the nucleus. Let me say that again because I did speak correctly. The size of the atom is roughly 100,000 times the size of the nucleus. So let's suppose we make the proton, the nucleus, let's just say some general atom, this is all rough numbers, but we make the nucleus the size of a tennis ball. So find a tennis ball sometime, or just make a fist with your hand. The size of a tennis ball, if that was the nucleus, if that were making some scale model, the atom would be about 4 miles across. The atom would be about 4 miles across if the nucleus is represented by a tennis ball. There's a big void inside atoms. There's a big region where there's nothing. We've got the proton in the nucleus, we've got the electrons in some outer structure of the atom, and there's a lot of empty space in between. And that's in this Bohr model of the atom, which, again, useful for talking about energies and light, but not completely correct. Okay, getting light coming out of an atom or coming into an atom and interacting with the electrons, that's key in terms of the emission spectrum and absorption spectrum. We need to know some facts about the electron in the atom. Well, this Bohr model calculated certain energy values for the electron orbits. And the closer we are to the nucleus, the lower the energy is. So higher energy for the electron as we go further away. You can do a little bit of a gravity analogy here. If you hold a ball up higher from the floor, it has more energy. If the ball is closer to the floor, it has less energy. So that is the scheme of things that Bohr used to work out the connection between electron energies and light. Then the Bohr atom says that the electron does not have a wide range of energies, all possible energies, but these orbits have definite energies, just certain energies. So the orbits close to the nucleus have a low value, and then we jump to some higher value here, we jump to some higher value here. And there is a trend in neutral atoms, and atoms that are not being bumped around too much, just kind of resting peacefully. The electrons have a tendency to move down to the lower orbits. Electrons have a tendency to move down to the lower orbits. You could think of, have a bowling ball on a hill with a roadway, a paved roadway. If you release that bowling ball, it'll roll down the hill naturally towards the valley. It's not a completely exact analogy, but that trend is the same. The electrons prefer to be in a lower orbit. So if we have an electron in an upper energy level, in an orbit that has more energy, it will prefer to be in the orbit closer to the nucleus and can drop down. As it drops down, there's a change in the energy of the electron. We have more energy here, we have less energy here. And Bohr said that this difference in energy becomes light. Light is energy. Light is carrying energy away from the atom. So this difference in energy becomes light. And the gap here between the orbits in energy, the energy gap, then gives a certain energy value to the light that comes out. We get a certain wavelength for that light. We get a certain energy, a certain wavelength for the light that comes out, and that energy and that wavelength is related to the energy difference between these two orbits, related to the energy difference. If I have an electron drop from a more distant orbit towards the nucleus, there's going to be more energy released there, and we'd have a shorter wavelength light coming out. And I'm going to go ahead and call them photons. In the process of emitting, this light is a localized package of energy. We'll call it a photon. When the light is out traveling between space, the model is that light is a wave. But when the energy is emitted and absorbed, we can talk about the photon model that Einstein developed. So here's our model, Bohr's model for how light is emitted from atoms. The electrons have definite energies in their orbits. When an electron changes orbit, it changes energy value, and the difference in those two energies is given to the photon. That light carries off a certain amount of energy. That light has a certain wavelength as it comes out of the atom. Another example of this, here's an electron in the third orbit, moving down to the second orbit, and in doing so, there's a certain difference in energy between these orbits that gives the light a certain wavelength and a certain frequency. If it's in the visible spectrum, a certain color. But the light that comes out, the wavelength of it, the color of it, is related to what change in energy occurred for the electron. Very important concept. The electrons have definite energies around the nucleus. When an electron changes orbit, it changes energy. It gives up energy when it moves towards the nucleus. It gives up energy and light is produced. Light comes out of the atom. Light is created by the electron dropping down to a lower energy level. So we have this atom, a dense positive nucleus with protons and neutrons in the nucleus. In the Bohr model, the electrons orbit the nucleus, and these electron orbits have definite energy values. The photon energy is equal to the energy difference between the two energy levels. And I've been talking about emission. I'm going to come back here. Let's talk about light being absorbed. Well, what if the electron is down here, and instead of this light going out, suppose this light was coming into the region where the atoms is. So there's a probability that this light will be absorbed by this electron. The energy of this light will be given to this electron, and this electron will move to an upper orbit. If the electron starts in level 2 and light with the correct energy comes in, the energy equal to the gap in energies of these two orbits. If the proper wavelength, proper energy light comes in, there's a probability that light will be absorbed by this electron and the electron will move to the upper level. That's the absorption process. The emission process, the electron moves closer to the nucleus. The absorption process, the electron moves away from the nucleus to an outer orbit. So Doppler effect. And how can we use light waves, wavelength and frequency, to determine the speed of an object? So we have a car here, and it has a car horn. That horn is sounding. The car travels off to the left. You can see, and this is semi-accurate, the waves get pressed together, not quite as much as they're showing in the illustration, but the waves get pressed together, and we're going to have, if you're standing off to the left here, you're going to have more peaks per second cross your ear. You're going to have more peaks per second. The pitch of the car horn will increase. You'll hear a higher sound. If you're back to the right, as the car moves away, the waves are generated by the car horn, and there's going to be more space between peaks of the wave. The wavelength is longer, the frequency is lower, fewer peaks per second cross your position, and you'll hear a lower tone. Now, possibly in your memory, you've been sitting at a car, in a car at a train crossing, and the train sounds its horn. As the train approaches you, the frequency, the pitch of the train horn is higher. As the train goes by you and moves away, the pitch of the train horn goes down, becomes lower. This is the Doppler effect. And astronomers use this for light. Light is a wave and has the same Doppler effect. Light that comes towards us, if a star is moving towards us or a planet is moving towards us, that light is pressed together in its wavelengths. We get a higher frequency light at the telescope. For a star moving away from us or a galaxy moving away from us, the light is spread out and we get a longer wavelength. And the amount of the spread here is related to the velocity of the object. So this can be used to determine speeds for an object going straight away from you or going straight towards you. This cannot determine the speed of an object that's going sideways to your line of sight, going left to right. The Doppler effect is only used if the object is coming towards you or is going away from you. And so some other applications of this, of course, with cars, you'd perhaps think of police using radar to determine the speed of your vehicle. And the police car sends out a radar wave, it bounces off of your car, and there are electronics in the police car that sense the frequency that comes back to the police car. And from that frequency, the electronics calculate your speed and display that to the police officer. So never speed. In a baseball situation, a radar gun is used to measure the speed of a pitch, kind of tell if the pitcher is getting tired or is at full strength. A meteorologist uses radar to determine the speed of water in the clouds and determine what direction the winds are blowing in the clouds. Again, that's a radar or a Doppler type shift. A medical application of using ultrasound to measure the speed of blood moving in veins and arteries. So there are several applications where this wave effect has practical applications. The Doppler effect is a change of wavelength, or you can say change of frequency, due to motion with the source of the wave moving away from you or towards you. We also get a Doppler effect if the observer moves, but we won't worry about that too much. Most of the astronomy applications, most of the motion is occurring where the light is being emitted. So moving away, we get what's called a redshift. The wavelength becomes longer. Moving towards, when the star is moving towards us, we get a blue shift. The star is moving towards us and compressing the wavelength, making the wavelength shorter. So that's Doppler effect. The wavelength and frequency change due to motion towards you or away from you. If the waves are getting longer because of this motion, that's because the object is moving away from you. If the waves are getting shorter, wavelength is getting shorter, the object is moving closer to you. We have And we can look at something, water waves being produced, and the source here is moving off to the left, and the water waves cast a shadow that's being photographed. But we have an illustration here. The wavelength is smaller in the direction that the source is moving. The wavelength is longer back here. So we get redshift back here, object moving away from us, wavelength is longer. Blue shift over here, object is moving towards us. So for stars, stars that are moving away from us, the light is redshifted a little bit. This is too dramatic. Light coming towards us, the light is shifted towards the blue a little bit. And what's actually used, of course, are the emission and absorption lines. We know the wavelengths of those lines by studying elements in the laboratory on the Earth. And if we measure a star and we find that the emission lines are longer, all of them being longer than what they are in a laboratory, we know that star is moving away from us. If we measure the wavelengths of the emission lines at the telescope and we find that they're shorter wavelength than in a laboratory, then we know that star is moving towards us. So here's a little bit of an example of this with the absorption lines. So let's suppose that this upper one is the measurements made in a laboratory, and at here measurements made in a telescope, and we're illustrating the movement of the absorption lines, or measurement of the absorption lines, that they're shifted towards the red, so what direction is the star moving? If on the upper top we're in the laboratory and we measure these wavelengths for the absorption lines, at the telescope we find that these absorption lines are in this position. What direction is the source moving? Well, you should analyze this and see that the absorption lines are shifted towards the red. They have longer wavelengths at the telescope for the object than they have in the laboratory. Longer wavelength means redshift, is the name given to that. Longer wavelength results when the object is moving away from us. Longer wavelength results when the object is moving away from us. So, how do astronomers determine types of elements in stars and galaxies? They measure emission and absorption lines, and we realize now that those emission and absorption lines are due to changes in the energy level in the atoms. Each atom has a different energy structure for its electrons. Each atom has different energy orbits, and consequently each atom will emit different wavelengths of light and absorb different wavelengths of light. The atom has somewhat of a fingerprint by virtue of its spectra, and astronomers can identify which element is present. Again, the wavelengths of the emission and absorption lines relate to the energy difference between electron orbits, and those are unique for each element in the periodic table. We use the Doppler shift to measure the speeds of stars and planets and galaxies. That's the amount of change in wavelength of these emission and absorption lines that provide a clue to the astronomers on the speed of objects toward us or away from us. So you should keep reading and asking questions on that, but that's where we're going to stop this YouTube video.